One of the most important checks that we can do on a RTD is insulation resistance, and it should be the very first one that you do before you do anything else to it is to check the insulation resistance. And what we're doing here is measuring how well the ceramic insulators here, and also where the lead wire connections are made back in this area, just to make sure that there's no moisture or contaminants that are causing shunting between either the lead wires or between these coils of platinum wire inside the sensing element. If we do have moisture in there, we can note that by a low insulation resistance reading, and the moisture or contaminants can cause shunting between these coils and a low resistance reading. Because electricity always wants to take the path of least resistance, and sometimes moisture or contaminants can be that path, and so it's not going to go through the platinum wire and give us a good accurate resistance and therefore temperature measurement. And probably 98 or more % of insulation resistance issues are caused by moisture getting inside the probe. The method that we use to test this is with a mega ohm meter, and we'll just bundle the lead wires and touch it with one of the leads, and then touch the other one to the probe sheath and note the reading on the meter. The test as a minimum should be done at 50 volts DC, and it should be greater than 100 mega ohms at room temperature. You'll see if you look at manufacturer specs, a lot of them are going to say they do the test at 500 volts and 500 mega ohms at room temperature. And for secondary temperature standards, it may be 1,000 mega ohms is what they're trying to shoot for. And for most industrial applications, if the insulation resistance is down below 10 mega ohms at the temperature that the probe is running at, there should be cause for concern, because it would indicate that something has gotten inside the probe, most likely moisture, causing a low insulation resistance. You really don't start to see any significant accuracy effects until you get down below roughly 1 mega ohm of insulation resistance. And we can run through a little calculation here to see what that is. And if we look here, our example, we've got really, really bad insulation resistance of just 0.1 mega ohm. And so that's going to result in a quarter of a degree C error in our measurement. So that's pretty significant. But if that were up at that 1 mega ohm, this number is going to drop quite a bit, and you can run through the math there and check that. But anyway, I just wanted to show kind of how this show how we typically would do this test. And we're going to start out with a probe that's actually bad here, and we've got this mega ohm meter, and we'll set this one to the 200. There's a 500 volt scale right there, and just connect one of the lead wires to the probe leads, and you can bundle them together, or typically just use one of them. If it's bad, you're going to get a bad reading typically. So, and here we can see this one is quite bad. We got 0.04 something, 5 something mega ohms. So this one has a really major problem. And we can see we'll end up getting kind of the same reading here if we bundle all these leads together too. We should end up with about the same reading here. Yeah, it's a little different, 0.08. So but that number, the scale would either read infinity or something above our 100 mega ohm minimum. And now this probe is a little different, and this one we'll check this, and this one should check out fine. So here we're not getting any reading. It's just it's kind of an infinite reading here where it's over the capability of the meter to measure it even. So this one we would consider as a very good probe. So so I guess we have one question here. I see, can we use a DMM for insulation resistance? And I guess the answer is yes, you can, as long as it has the capability of measuring at a high enough level to ensure that the part is good. I think the ones that I see frequently are, they're not going to go up past 100 megohms. They're more kind of in the 10 meg range. But you know, if you do have one that, you know, has the capability for doing multiple tasks, you know, you certainly can use that. So the other thing too, I see, Jeff, I wonder if we could just back up here a little bit too. We had another question about the
sure.
The copper block inside the calibration bath.
Yeah, there's a question is, you know, what's really the effect of that copper block, and is that something that we would recommend, or so someone hasn't necessarily seen that before, so they're wondering what the improvement in stability might be.
Well, you know, for our, like in our lab, what we're trying to do is get to the best possible stability and to minimize any kind of temperature gradients. But we're also doing batch processing of temperature probes, and so the copper block helps with that in that it allows that really high uncertainty of measurement within that bath. You know, if you were just going to do one probe, I'd say probably don't bother with it. But if you're doing multiple probes at a time, the either copper or an aluminum block works well too. Does help minimize the temperature gradients within the bath and will help you achieve a lower uncertainty measurement. So, but I don't know, that was a good question. I just wanted to cover that here before we jump on to the ice bath testing, and also to see if anybody had any other questions about insulation resistance. It looks like we probably just had the one about using the DMM in place of a dedicated megohm meter. So,
yep, and just a reminder, if you do have questions, go ahead and type them into the chat.
So, after we get a good ice bath or a good insulation resistance reading, the next test I like to do is in an ice bath. Now, an ice bath that's put together correctly, you can get really good accuracy out of these, and it could be in the range of like plus or minus 0.002 degrees C. They're quite easy to make up and very accurate, and it's also the point that the manufacturers test when they build the sensors, and so you'll be able to verify the original specs for the sensor by doing this ice bath check. And if you have a lot of fancy equipment like this, you know, multi decimal place meter here, and it's got the lead wire compensation that it does automatically, you know, that's great. A nice stainless steel dewar here with this one actually has a stirring motor in it that circulates the water throughout the ice to give you even a little better accuracy. But really, to do a quick verification, you know, you don't need a whole lot of fancy equipment. And mostly the important part is to just to use the crushed ice, purified water, and some sort of an insulated container. And if we just take a look here, this, you know, you just go steal somebody's lunch cooler and fill it full of crushed ice. And when we're making crushed ice, we like to use distilled water or purified water and chop it up so it's, you know, usually the chunks are maybe a 1/4 inch diameter at most. And then make sure it's packed well into the container. And then you want to add enough distilled water to just fill in any gaps that are in the ice chunks, and to get it up to within maybe an inch or a half inch of the top of the ice. You do not want the ice to float. You just want it to be packed tightly in the container, and then just have enough water to fill in those gaps. Then we'll take our temperature probe and insert it, and it's a good idea to insert it at least probably about 4 inches is a good number. You don't want it to touch the bottom of the bath. Then we just hook up our lead wires, and here we're reading, about 100.1 ohms. And now we want to eliminate the lead wire resistance. So we go over to the 2 red lead wires, and we're seeing that we've got about 0.2 ohms of resistance. And so if we were to subtract that from what we see between the white and the red lead, that's going to give us our resistance of just the platinum sensing element, and that's what we want. And so for this meter, it's only got 1 decimal place resolution, and so if we take that reading and subtract our couple tenths of an ohm, we're still within what would be a Class B sensor tolerance of, it would be 99.9 to 100.1 ohms. So we're still within that range. So this would be what I would call a very crude verification of the performance of the probe. To get something a little better, you'd need a little better meter with a little more resolution on it. Now, if we were to I just wanted to show the importance of using a large enough ice bath. Here we just filled a coffee cup full of ice, and we're going to demonstrate here that this really isn't enough ice, and the probe, we shoved it down to the bottom of the cup, and we're going to get some different numbers here. We've got it's 100.2 instead of 100.1. So you can see that having a large enough container of ice and having it well insulated is important. And this number is going to jump around a little bit, and it's just kind of a bad way to do it. So again, it's got to be an insulated container, enough ice to fill it up completely. Pour in enough water to come up to within about an inch or a half inch of the top of the ice. And then when you place the probe in there, you need sufficient immersion length to overcome any kind of stem conduction, which for 1/4 inch diameter probes, it's usually about 4 inches. And you want to make sure that the probe does not touch the bottom of the ice bath. You need to leave a little bit of space at the bottom. So, real simple check to do, and gives you a good, accurate number of how it compares to the original manufacturer's specifications for it. Now, the 2 standards will have either the Class A or Grade B and the Class A or Grade A sensors. And right down here at our 0 degree C vertical axis here, we've got, or horizontal, we've got our best or tightest interchangeability, because that's where the manufacturers adjust the sensing elements when they're building the probes and putting it all together. But as we go away from 0 degrees C, that tolerance band opens up. And if you look at the lines here, you can see the IEC standard is a little looser tolerance than the ASTM does. And we can use these equations to actually calculate the interchangeability at any given temperature. So if we know that we purchased, let's say, this Grade A sensor, we can take and plug in the temperature of interest here. If and it's the absolute value of temperature. So if it's a negative temperature, you would just drop the negative sign. Do the math, and it'll tell you what the interchangeability is at that particular temperature. For 0 degrees C, of course, this part of the equation drops off, and we just have this plus or minus 0.13. So if we were doing a grade A RTD in the ice bath, we'd want to make sure that we hit that plus or minus 0.13. If it's outside of that range, it means the probe has drifted, or there's something else has happened to it. It got dropped, or you should consider replacing it at that point. Kind of wanted to reiterate here. First off, check the insulation resistance, then do the ice point, and then there's really no hard and fast rule as to how frequently you should be doing these tests. It's really up to your own level of confidence in that point, and it might be a safety issue, product value, and the characteristics of the process, what it's doing, vibration, shock, those kinds of things. They are all going to affect the long-term accuracy of that temperature probe. So, you know, I should mention too, I had a question a few days ago about temperature probe in a freezer that I forget what it was, running at some pretty cold temperature, and kind of difficult to get at and to check it, and they thought it probably hadn't even been checked for quite some time, which is a little bit concerning. But again, they're, you know, part of the process where you can't get at the temp sensor. That's going to actually help dictate maybe your calibration cycle, right or wrong. In that case, I think it probably was something that maybe should have been done more frequently than what had been done, but it was in a situation where it was pretty much a constant temperature, and it was on the cold side, so the temperature probes tend not to drift very much in those kinds of situations, and you know, it may be, your frequency might be measured in years rather than months.